This lecture is about ventilation and air contaminant fundamentals. So this first lecture will be just about the basics of what ventilation is and what common air contaminants there are and how they affect our bodies. The second lecture that goes along with this one will be about how to achieve proper ventilation in an airborne hazard environment and the best ways to go about controlling for ventilation hazards. For these lectures, like I said, we'll be discussing airborne contaminants and how to control them. But before we get into the details of what the contaminants are and how to control them, we first must understand some basics of how air and ventilation work. Ventilation is essentially just the movement of air. There are different factors that affect this air movement, including pressure and resistance, which is also pressure drop. And the concept of air movement and how to direct it is actually pretty complex. But for the purpose of this course, we're just going to go over the very, very basics. Pressure and air movement are very important concepts when it comes to learning about ventilation. Air always moves from high pressure to low pressure, except for when you're talking about air movement right at a fan. When there's more pressure, air moves at a higher velocity, so the air moves faster when there's more air pressure. This is important to keep in mind for when we discuss control methods later, as many of the methods that we discuss utilize pressure changes to move air contaminants out of the environment. So as you can see in this example picture on the slide, on the left side and down in the left corner is an area of higher air pressure. And then on the right side, there's an area of lower air pressure. And there's this pressure gradient that is built up between the two areas. So the air moves from the area of higher pressure to the area of lower pressure. And this is what we perceive as wind. So this is air movement, wind. It's the same kind of thing. So wind is always going to be moving from higher pressure to lower pressure out in nature. Atmospheric air pressure, which is also known as barometric pressure, is the pressure within the atmosphere of the Earth. Or it's also known as the measurement of the weight exerted by air molecules at a given point on Earth. So you can think of the air around you as a column of gas above you. So the air that's directly around you is a column of gas above you, and the pull of gravity on all of the molecules in that column of gas applies a force on us that we experience as atmospheric pressure. Standard atmosphere, or ATM, is a unit that can be defined by a lot of different measures of pressure, and the ATM unit is roughly equivalent to sea level atmospheric pressure on Earth. So Earth's atmospheric pressure at sea level is about 1 ATM. This sort of air pressure is directly related to things like altitude, temperature, and air composition. So for example, air pressure is greatest at the ground and decreases with higher altitude because at higher altitudes, the column of air, remember the column of air that's around you, it gets shorter and the density of the gas particles decrease. So as the individual gas molecules warm, they take up more space, which causes gas to be less dense, meaning air pressure tends to decrease with increasing air temperature. So like I said, there's these different factors like altitude and temperature that can affect the air pressure of the atmosphere. When we discuss air movement or ventilation in an engineering sense, so in the sense of we're trying to control for it in an occupational setting or a residential setting, we can also describe it as airflow, which is the measurement of the amount of the air per unit of time that flows through a particular device. This can be described either as volumetric airflow rate, which is the volume of air per unit time, or it can be described as mass flow rate, which is the mass of air per unit time. Airflow can be induced mechanically or take place passively, and you'll see how the methods that we discuss later will utilize one or the other or a combination of the two. Another way that a structural engineer may consider airflow is thinking of air changes per hour, or ACH. This is something that if you do kind of more reading on ventilation, or if you decide to pursue this in the future for your career, you'll come up across this term a lot. So ACH is a calculation of how many times per hour the entire volume of air in a given space is replaced with a supply and or recirculated air. So basically, how many times per hour is all of the air in the room cleaned out and replaced with recirculated or new air? This can also be referred to as air change rate or air exchange rate. There are a lot of different kinds of equations that go along with calculating airflow, air velocity, and air pressure measurements, and design. But since this is just a 1-week lesson on ventilation, we're going to mainly focus on more qualitative aspects of air contaminants and ventilation control. As you can see here on this slide, I pulled this slide here, this figure, from a talk about the best ventilation standards in situations like COVID exposure. So this is, you're probably aware that after, starting in 2020, there were a lot more conversations about how well are we ventilating our indoor spaces in order to protect people not just from occupational hazards, but from things like COVID or other viruses and things like that as well. So in this talk, they were proposing that the ideal air change per hour, the ideal amount of air changes per hour would be 6. And then kind of a low rate of air changes per hour would be less than 3. So when you're thinking about designing a building, whether it's for, perhaps for a hospital or maybe for some other manufacturing facility, something along those lines, you should be really aiming for at least 6 air changes per hour. The normal composition of air is primarily 78% nitrogen, 21% oxygen, and then much smaller levels of carbon dioxide, argon, other gases, and then there's also water vapor in the air, which gives us measurements of absolute humidity and relative humidity. However, we are often exposed to airborne contaminants, whether we are at work or at home or just taking a walk outside. Talk about pollution. Pollution is the presence of airborne contaminants in our air that we are breathing. So the focus of these lectures is how to control, how to fix those airborne contaminants that are present in this air that we're breathing. There are several basic categories of airborne hazards. These are dusts, fumes, mists, gases, vapors, smoke, and oxygen deficiency. And I'm going to discuss each one of those as well as give some examples in the next slides. So dusts are particles that are formed or generated from solid, organic, or inorganic materials by reducing their size through mechanical processes such as crushing, grinding, drilling, abrading, or blasting. So essentially, you're taking some sort of solid material and you are breaking it down into really tiny particles that are released into the air. Some examples of inorganic dusts would be silica, asbestos, and coal. And examples of organic dusts would be dusts that originate from plants or animals. And it's important to note that a lot of organic dusts often contain several other hazardous substances along with the dust, such as fungi or microbes. So I think when we think of dust in an occupational sense, we're thinking of things like asbestos or things that are kind of a byproduct of the manufacturing process and things like that. But really the organic dusts can be just as hazardous because they can often contain a lot of these other materials, substances within the dust particles. So this is a picture on the slide of an example of coal mine dust. So coal miners are exposed to dust from the coal, but it's not just the coal. It has these other active metals and things like that and it's not just carbon that they're inhaling. So it has these other materials that are in the dust that they're inhaling, and they get down into the lungs, and as you probably know, cause a lot of lung issues. Fumes are particles that are formed when a volatilized solid, such as a metal, condenses in cool air. This physical change is often accompanied by a chemical reaction, such as oxidation. So for example, when cold metals are heated up during the welding process and melted, this generates welding fumes. So in our lecture about non-ionizing radiation, we learned about one of the hazards of welding is the light that the welding workers are exposed to. So they have to wear special welding shields, and the heat obviously is part of that as well. But there are also these dangerous fumes that can be created during the welding process as the metals are heated up during this process. So not only do they need to protect their eyes and their skin, but they also need to have some respiratory or ventilation protection. Mists are formed when a finely divided liquid is suspended in air. And then these suspended liquid droplets can be generated by condensation from the gaseous to the liquid state, or by breaking up a liquid into a dispersed state, such as by splashing or foaming or atomizing. A very common example of mist in an occupational setting is oil mist, and this is something that has become a focus of occupational hazard control. So oil mists are often created when metalworking fluids come in contact with fast rotating machinery. So this is a picture of an example of that. So they often use these fluids while they're grinding metals and things like that in order to reduce heat, reduce dust, and those sorts of things. But these fluids then, because they're coming in contact with this fast rotating machinery, get dispersed into tiny droplets, which creates this mist. So it creates an oil mist. There's a lot of questions around how is the oil mist affecting the respiratory tracts of the workers who are exposed, and what are the best ways to control for this. Gases are formless fluids that occupy the space or enclosure that they're inside, and can be changed to the liquid or solid state only by the combined effect of increased pressure and decreased temperature. Vapors are a gaseous form of substances that are normally in a solid or liquid state at room temperature and pressure. Vapors can be transformed to the liquid phase either by increasing the pressure or decreasing the temperature. So an example of vapor is just a really simple, common example, water vapor. So that is responsible for humidity. So you can feel how the presence of that water vapor, an increase in water vapor, can change the air that's around you. Smoke is another really big, very common air contaminant that is produced a lot in a lot of occupational settings, as well as just everyday settings. If somebody is burning foliage out in their yard, it's affecting, if it's your neighbor, it might affect you, that sort of thing. Smoke consists of carbon or soot particles that are resultant from the incomplete combustion of carbonaceous materials such as coal or oil. And smoke actually generally contains droplets as well as dry particles. We often think of smoke as just like a very dry, kind of dusty air, but it often contains droplets as well. And then oxygen deficiency is something that is important to consider when we're talking about ventilation. It's not what you would commonly think of as an air contaminant because it's kind of more of the lack of oxygen and lack of air instead of the introduction of a contaminant into the air, but it's still something really important to consider when we're talking about ventilation. So an oxygen deficient atmosphere is something that is defined as having oxygen content below 19.5% by volume. This can occur in a lot of different confined spaces, such as storage tanks, drums, tank cars, bins, septic tanks, and underground utility tunnels. So these are things that, if a worker is going to be spending time inside one of these environments, the structural engineers need to take this into consideration to make sure that the ventilation is appropriate so that these employees do not work in an oxygen deficient environment. There's a wide range of potential health effects that stem from exposure to airborne contaminants. These can include asthma, lung cancer, or other sort of cancers along the respiratory tract, COPD, mesothelioma, and silicosis. This is why it is very important to utilize proper ventilation hazard controls to prevent these health conditions, particularly in occupations that generate a lot of airborne contaminants. And these are things that weren't really appreciated in a lot of the kind of unregulated industry until the last several decades, when people started to realize that there are consequences to breathing in these sorts of airborne contaminants. And so, as you will learn about in the last third of this course, there have been a lot of regulations that have been put in place in order to protect workers, as well as protect residents of communities where there may be, for example, a lot of chemicals put into the air due to some manufacturing process of a factory nearby.